Decades ago, physicists imagined a tantalizing technological future powered by metamaterials, materials designed by humans to manipulate the flow of energy in incredible ways. The key to this future? Computer simulations. Calculating the orbits of a handful of electrons could reveal which metamaterials were possible. There were equations for this, famous ones which could simulate systems of dozens of electrons. But the search for new materials could potentially require simulating the motion of thousands, creating an impractical demand for specialized computer resources. For John Perdew of Tulane University, this was unacceptable. For a young John Perdew, life was a numbers game.
In high school, I started to get interested in mathematics because I had a very good geometry course. And in that course, I saw that you can combine intuition and visualization with logical arguments to reach a true statement. That impressed me a lot.
Math was a roadmap to answers, an avenue out of his sleepy hometown of Cumberland, Maryland, that went straight to the quantum heart of the universe. Equations had never failed him until 1973, when Perdew, with a PhD in physics from Cornell, began wondering about the possibilities of metamaterials.
Metamaterials get their unique properties from how their electrons move and interact with one another. There's no way around it. To design metamaterials, we need to simulate the interplay between sometimes hundreds of electrons. For Perdew, it was like trying to forecast the path of every bee in a swarm.
I'm a sort of obsessive thinker. When I have a problem to solve and it's an important problem to me, I just keep thinking about it until I solve it. And if I never solve it, I just keep thinking about it forever.
Stymied behind a mountain of math, Perdew wondered, was there a way around it? The answer was yes, kind of. A colleague introduced Perdew to density functional theory, or DFT. It was a way to approximate electron motion, to look at the shape of the swarm rather than the individual bees. There were major drawbacks. For all materials but metals, DFT simply wasn't accurate. Perdew got to work on a groundbreaking overhaul of DFT that would change the world.
So basically, the computations allow us to make predictions about what materials can exist and what properties they have. In chemistry, you can design molecules on the computer. In condensed matter physics, you can design solids on the computer with properties that you want.
Physicists once dreamed about the endless possibilities of designer materials. Because of Perdew, that dream is now reality. Improved DFT has been used to discover lithium battery materials, superconductors, and components for quantum computing. The ability to predict molecular crystal structures is opening the gates for new revolutions in medicine. And as modern DFT sheds light on hydrogen storage for propulsion, DFT may just bring humanity a step closer to the stars. As for Perdew, the same as always. Solutions, one after another, and sometimes the other way around.
I'm working now on a research problem that I started more than 40 years ago and made some progress on then, but the solution's not complete yet, so I'm not satisfied.